kudos to the Understand Energy team for including energy efficiency as one of the resources in a general energy course. There's Energy 101 type classes all over the country, and almost none of them even mention energy efficiency as a resource, let alone, the demand side in general. So I think that's kind of half the battle there. So here's an outline of what I wanted to talk about. First, just why we care about energy efficiency and its importance. The roadmap to the resource is how we use energy, so you have to be kind of a nerd and learn about that. How we identify energy efficiency measures and their potential. Talk about what we call the barriers to energy efficiency, which is kind of why all of this hasn't already happened and why we have to take specific actions to enable it. And then a couple of themes of policy and implementation ideas having to do with, first, codes and standards, and secondly, energy utility-based programs. And then wrap up with a little big picture about efficiency in the process of decarbonizing the energy economy. So, going back in history, as Diana said, I'm kind of an old guy, so I remember back in the 70s when energy first came onto the public consciousness and arose as an issue. And the question was really, are we going to run out? Is there enough oil in the world, for example, to maintain our economies and our lifestyles? And Elvis met the president. That was important too. But then over time, we started to think a little bit more about the options available, and the idea of energy efficiency resource arose in particular with folks like our colleague Amory Lovins, with whom I co-teach a course here. Also, the late, great Art Rosenfeld, who was a physicist at Berkeley. I think he was Enrico Fermi's last PhD student, but also quite a pioneer on both the technology and policy of energy efficiency. And Amory published a paper back again in the 70s, in the bad old days, the dark ages of energy thinking. And at the time, the conventional wisdom was that energy demand in the US really needed to continue growing more or less exponentially to the point where we had a nuclear power plant on every street corner by the year 2000 or 2010, way out in the future from that perspective. And Amory asked two questions opposing that conventional wisdom. The first was just like, what in the world are we going to use all that energy for? And that was a hard one to answer. And then the other was, well, couldn't we meet those needs that energy is supplying with another approach, using the energy much more efficiently and thereby demanding less of the resources? And that turned out to be a relatively easy question to answer. And of course, at the time, that was complete heresy. There's my cursor. But Amory was widely criticized and pilloried by the entire energy intellectual establishment and industry at the time. But it turned out that his projection, which is the blue line, not the red line, turned out to be a lot closer to reality, which is the black line, over time. And so you might argue, and some people do, that he was right for the wrong reasons, but I got to think that's still better than being wrong for the right reasons, right? Anyway, that paper and that question that Amory asked and answered was really a paradigm change. And the paradigm, as it was before that happened, was really that the energy system looked kind of like this. There were resources out there, and there was exponentially growing demand for the commodities that we could extract those resources and convert them into, and we really needed so many more of those resources, and of course all the environmental impacts that they lead to, that we were stuck with that level of demand and chasing the supply and its impacts. So the additional question that we asked was, well, is it really those commodities that we're after? Or is it the right-hand side of the chart here and the energy chain, the downstream or demand side of the energy chain, where it's not liters of fuel or kilowatt hours of electricity that we benefit from. It's really traveling down the road or illuminating our work or comfort in our buildings or productivity at the office. And in between that commodity and that service, there's a whole range of end-use technologies that have varying efficiencies, and maybe we could intervene and improve the efficiency with which we're using that energy that would then result in meeting those demands for the services that we want and need with the same or less of these commodities and all of those economic and environmental and security impacts that they cause. So it was really a new way of thinking about energy systems, that the product is not the commodity per se, but rather the service. It's the cold beer and the warm showers that we really need. Well, unless you're English and you like it the other way around. But the point is that it's the services rather than the commodity, and how do we supply those services in the least cost way? Is it with another kilowatt hour, or is it with a negawatt of energy efficiency? Okay, so that's kind of the paradigm shift that occurred, and it was really led by Amory, and a bunch of us jumped on the bandwagon. And it leads you to the question of, okay, well, how do we find potential to improve energy efficiency? And at this point, you got to start being kind of a geek and think about how energy is used, because that really becomes the roadmap. And you start going through statistical data like that published by the Energy Information Agency of the US Department of Energy, and say, well, where's all the energy being used? And then how can we improve that? So if you look at energy consumption in the US by economic sector, there's actually kind of four nearly equal sectors in transportation, industry, residential buildings, and commercial buildings. And they all have kind of different breakdowns of how you use energy. And so you really need to dig one layer deeper and say, well, what is it that you're actually doing in that building or that industrial plant or that vehicle? Well, the vehicle's pretty straightforward. But in buildings, there's a whole range of different end uses that provide us with those services, the thing that we actually want, the cold beer and warm showers. And as you can see, a lot of it has to do with space conditioning, with space heating, space cooling. Water heating is also another significant one. And of course, the need for heating and cooling varies by climate, but the total is usually pretty consistent. Some climates need more heating and almost no cooling. Others need mostly cooling. And either way, they still become significant residential energy demands. Now, if we look at electric energy specifically, we could think about the different things that electricity goes into. Heating is one, lighting, illumination, particularly in commercial buildings is important, all our electronic toys, and motors for electric-driven motor drives. Any guess which is the most important globally that uses the most electricity? Well, if you're not willing to guess, I'll just tell you. It's the motor drives. And the reason for that is that these motors run lots of different kinds of systems within industry, within buildings. They run the heating and cooling equipment. They run pumps for irrigation. They run conveyor belts. They run compressors and all kinds of machinery and production equipment in industrial facilities as well. So the simple ratio of motor efficiency in buildings and industrial facilities around the world is a really key driver of energy efficiency and an important source of efficiency potential. Let's look at how we actually define energy efficiency measures, the resource itself. And the little cartoon here with the lightsaber that's a compact fluorescent. It's already a little bit out of date, but that's kind of consistent with the theme here. So in order to understand the efficiency potential in buildings, for example, we need to think about how energy is used, what those end uses are, and we tend to start categorizing even more precisely than just buildings per se. For example, residential buildings where we live and commercial buildings where we work are similar, but pretty different too in their size and the way that they're occupied, night versus day, the types of equipment, and therefore the need for different energy services. We also tend to distinguish between existing buildings and new buildings. Now, in a new building, you have lots of opportunity to improve design, and I'll talk about a design approach that we use and recommend. But you can really achieve a lot of efficiency improvement, maybe a net zero, maybe a net positive energy building with some pretty simple approaches. In existing buildings, well, there's a lot of inefficiency, believe me. You pretty much trip over inefficient operation in buildings as well as old inefficient design, and there's lots of ways to improve those systems, but it's a different and a more challenging problem. And there's different approaches to it. For example, you can just replace equipment with more efficient units, but you can also look at the way the building is controlled and operated and typically find simple operating efficiencies that can improve performance and reduce costs by 10, 20%, often without even any significant investment. We look at the different end uses. We look at lighting. We look at heating, ventilation, and air conditioning, HVAC, HVAC, people say, in buildings, and the electronics and so forth. And then we typically also distinguish between those types of equipment that use energy and have a level of efficiency and often can be improved, and the building shell itself, the envelope of the building, the walls, floors, doors, windows, roof, all of those surfaces that communicate heat and sometimes light in and out of the building, and the rate at which they communicate energy with the environment, whether it's losing heat in a cold winter day or whether it's gaining solar radiation on a hot summer afternoon, that can affect the energy performance, and that can be designed well for a new building, and it can be improved or retrofitted in an old building. And so we've had some real advancements over time, partly in technology and partly in the way we think about buildings. When we think about efficiency in lighting, for example, we always remind clients that the first thing you want to do is make sure you don't need any more light than necessary. So you try to harness the daylight that's already available, that's free. And you also try to use the surfaces within the space to be designed in a way that bounces and reflects and diffuses light in a way that's both sufficient and available for your task, but also not too bright or too glary or too contrasty. And then you move on to the hardware and try to figure out the more efficient lighting sources, and that's where we really had some pretty amazing breakthroughs. And then you start thinking about operation, not leaving on unnecessary lighting, for example, or automatic controls to accomplish that same savings. But the lighting hardware has really been kind of an amazing story. And the breakthrough is really the LED, light emitting diode technology. And it was actually one of the first very simple efficiency measures that we had for like exit signs in theaters. Like you'd be in a movie theater and you'd see that kind of little green glow down in the corner. It said exit. So if there was a emergency, you knew where to get out even though it was dark. Well, it turned out those had like 50-watt incandescent lamps, and they could be replaced easily by an LED lamp that used like 1 watt. So it was a big saving proportionally. But why did we do that? Well, we had green LEDs and we had red LEDs, but we didn't have blue LEDs. And without blue, you can't get white. Without white, you can't do much other than exit signs. But later, in the 2000s, thanks to a Nobel Prize winning advancement in semiconductors, they were able to invent a blue LED with which we could make white LED light sources, which made we could make every type of light source, not only much more efficiently, but also beautifully controlled and controllable. And so now we have really the potential to get, on this chart, it shows us going from about 15 to close to 100 lumens, that is light units per watt of energy. Now we can get close to 200. with LED lamps, they're so efficient. So that's one area where we've really seen a steady decrease in the demand for energy while improving the service. Heating and cooling is more complicated, as I explained, in the different types of buildings. You really have to look at how you approach it. But again, the process we recommend is always first to mitigate the load, the demand, the need for the heating and cooling. How? By making the shell more efficient, by avoiding unnecessary sources of heat when you're trying to air condition the building, and then to look at the equipment and to try to find more efficient equipment and then to control it more precisely, and so that it's serving the load and using energy only as needed. And then, even when we have the more efficient equipment, we can consider the operation and use periodic commissioning or instrumented diagnostic checkups on buildings to ensure that they're actually working as designed, regardless of the level of efficiency. And you can typically find ways to save more energy dollars that way. In the building shell, there's also new technology arising all the time. The biggest source of heat loss and heat gain in buildings is the windows. And the unit that we use in our antiquated Burmese units of inches and pounds and so forth to measure thermal resistance, which is analogous to electrical resistance if you think of heat flow as a circuit. A single glaze, simple old-fashioned window has a thermal resistance of 1, uno, and a double glaze 2, triple glaze 3, etc. Very simple like that. And so you can massively reduce the heat loss and gain of windows by using more layers of glazing, but after a while that gets to be kind of difficult in terms of cost, but also just the practicality of adding more than a couple sheets. But we can also put in low emissivity and reflective, heat reflective, thermally reflective glazing coatings on the surfaces of those glazing sheets. We can fill the gap with gases like argon that retard thermal convection and thereby increase that thermal resistance, that R value, beyond 2 or 3 up to 5 or 6 or even 8 or 9 with advanced windows, and thereby improve the performance of building heating and cooling. Now that's mostly in new buildings, but in existing buildings, upgrading the building shell is pretty difficult. But even there's been some interesting advancements recently. In the Netherlands, they have a program called Energiesprong, which means like energy leap or leap forward, where they're trying to do mass retrofits of multifamily housing, where they use a very advanced laser-guided measurement of the building's skin that then is the template for making factory manufactured exterior insulation that's brought in, and like in a day or two, they completely re-insulate the entire building shell, retrofit the windows that are already properly cut out and sized and so forth, install advanced heat pump heating and cooling equipment, and put solar on the roof, and they go from an energy hog to net zero in just a day or two of installation, and the whole package is financed with low interest financing, subsidized partly by the state and the energy utility, so that it makes it cash flow positive from day one for the occupant. And this type of approach is being investigated for importing to the States, and so watch that space. So that's a little bit about the building shell. If we talk about heating and cooling equipment, one thing that might be familiar to some of you, particularly if you're from the Northwest, is electric baseboard heating or resistance heating. It's one of the simplest and, in terms of first cost, cheapest ways of heating a space. It turns out it's pretty inefficient, which at first you'd say, well, now wait, all the electric energy that goes through that baseboard comes out as heat. It's 100% efficient. You can't do any better than that, right? Well, the answer is wrong. Actually, we can do a lot better. And so resistance electric heating is actually considered really inefficient, and I'll refer to it as bad electric heat. And for a long time, we actually recommended for energy cost and environmental performance to switch to gas heating because you could get pretty close to the same efficiency with a cheaper and, until recently, lower carbon energy source. And so electric resistance heating is still considered bad electric heating, and the alternative being typically gas furnaces, a forced air system where your furnace, which now we can get over 90% efficiency with condensing gas furnaces, which is pretty good. And depending on how the delivery system is designed, you may or may not have substantial losses in the ductwork getting to the actual end use. But we're no longer recommending switching to gas heating. In fact, we're starting to think about switching from gas back to electricity, or at least in situations where you have the opportunity to replace the heating system, to reconsider electric heating, but not bad electric heating. Rather, we want to switch to good electric heating, which is using heat pump technology. And the thing about a heat pump is it doesn't have an efficiency of 100%. It has efficiency of 200 or 300 or 400%, a multiple of the energy used as electric input coming into a heat pump can be delivered as heating, which sounds kind of crazy, impossible, like maybe violating some physical laws. But let me explain how that works for those of you who aren't mechanical engineers. But the point is, with good electric heating, now we can actually provide less expensive heat and much less carbon intensive heat, particularly if we use relatively clean sources, renewable sources of electricity to run our good electric heat when we've got a heat pump. So how does a heat pump work? So the laws of thermodynamics, they call economics the dismal science, but I think I work in both economics and thermodynamics, and they're kind of equally dismal, because the first law of thermodynamics is you can't win. Energy cannot be created or destroyed. It can only be conserved, and so therefore you can transfer energy from one place to another. You can transform from one source to another, heat, fuel, electricity, etc. But you can't create energy. So you can't win. Well, that's okay. But the second law is you can't even break even. And it's a more complex and subtle set of math and relationships. But the bottom line is that the second law of thermodynamics tells you that there's a quality to energy, and there's high quality energy that can do physical work, like electricity can often perform physical work with near 100% efficiency. And then there's lower quality energy, namely heat. And the lower the temperature that the heat's delivered from, the lower the quality. And that makes a difference when we're thinking about heating buildings. Because if you think about it, heat will flow from warm to cool. So if it's warm in your house and it's cool outside and you're too warm, you can just open the window and the heat will flow from warm to cool. The air will mix, it'll get cooler inside. It'll get incrementally warmer outside as the energy balance, the first law, occurs. But you can achieve comfort that way. But now, if it's warm inside and cool outside, you can't move heat from cold to hot. You can't warm yourself. Even if you respected the first law, the second law won't let you go from cold to hot unless you put some energy in. Okay, well, that makes sense. But the trick is you don't have to put all the energy in. You only have to put in enough to make the transfer happen, and you can get the sum of the energy you put in plus the energy you transfer. So let's see how that works. You're probably familiar with air conditioners, and a heat pump is really just a reversible air conditioner, but think about a refrigerator. It's also the same technology. So let's say you take your refrigerator and you wheel it over to like a sliding glass door or something, and you set it so that the heat rejection coils are on the outside. Okay? So instead of cooling the inside of the refrigerator box and warming your kitchen, you're now opening the door and cooling your space. So you're air conditioning. And on the outside, you're rejecting heat to the outside. So you're moving heat from inside where you're cooling to outside where you're actually warming a little bit. And you're running the refrigerator and putting some energy in. So you've transformed your fridge into an air conditioner. See how that works? It's the same technology. I mean, it's really the same components even. Okay, so that's air conditioner, refrigerator. Now let's take the fridge and spin it around the other way on the right side. Okay, so now you're cooling the outside air marginally so, and you're rejecting heat into the space. You're heating the space. So now you're moving heat from cold to hot, which we said you can't do spontaneously. If you open the window, it won't go that way. But we're putting that extra energy into the fridge, into the compressor, and running the vapor compression circuit and turning it into a heat pump. We're borrowing heat from the outside, adding some energy to it, and delivering a greater amount of heat to the inside. So that's what a heat pump does. And it's really, again, the same technology as we see in air conditioners and fridges. So to get a little more detailed and a little more geeky about it, let's run through how the cycle inside the box works. And it's taking advantage of one very simple property, the same property that we use in steam engines, which is that a substance like water or the gases that they use in air conditioning equipment evaporates or boils. It changes phase between liquid and gas at a different temperature depending on its pressure. And the higher the pressure, the higher the boiling point, the higher the point at the temperature at which that phase change occurs. We take advantage of that in steam engines, for example, and we take advantage of it in air conditioning equipment. So let's go up to the upper left-hand quarter and start our cycle with a liquid that's very cold, okay? It's so cold that it's colder than the outside air, okay? And we run it through the evaporator, which is a heat exchanger. It's just a coil of metal that easily transfers heat between the fluid in the system and the outdoor air. But because it's so cold, it's heated up by the outdoor air. That cold outdoor air, although it's cold, it's still warmer than that liquid that's then evaporating, boiling in the heat exchanger. So we take heat from the cold outdoors by starting with a colder fluid. And we actually boil it at a very low temperature because it's at a low pressure. Okay? So we take our low pressure, cold gas and boil it by taking heat from the not quite as cold environment. Okay, well, we can't do much with that. We've still got pretty cold gas. That's when we put the energy in. We run our compressor to raise its pressure, which also raises its temperature. Okay, so we have to put some energy in there, and that's where the denominator in the energy efficiency for a heat pump comes in. And now we've raised the pressure and the temperature of that gas, so it's now warm enough that we can heat our space with it. We can run it through another heat exchanger in the space, and because it's so warm, it will transfer heat to the space. The space warms up. That's what we want. We want our heat. That's our warm shower, so to say, our warm air. Okay, and that cools down the gas that we're using for the heat transfer, okay? And it actually starts to condense, go back to a fluid, but still at a high pressure, okay? So now we've got warmish liquid. We can't really do much with that because we want to collect heat from the outside. But now we can get it cold again by doing the same trick in the other direction. We lower its pressure by just running it through an expansion valve. In a big system, you could even extract some energy doing that. But that cools the gas down as it drops in pressure, closing the cycle, and we can start over, bring heat in, pump up the pressure, dump the heat in the space, expand it, and round we go, each time gaining heat from the cold outdoors and then delivering more heat to the warmer indoors. That amount is the sum of the heat we extract from the outdoors and the energy that we put in as electricity. That's what the first law tells us. And so our efficiency is the sum of those two things divided by just the electric input that we have to pay for. So it's more than one. And we don't like to talk about an efficiency of 200%. That kind of sounds like you're cheating, right? That can't really be in physics. That doesn't allow that. So we call it a coefficient of performance, a COP. So the COP of a heat pump might be 2 or 3 or even 4, depending. And what it depends on, the thing that drives the potential for a higher efficiency or a higher coefficient of performance, heat pumps and air conditioners and so forth, is the temperature difference that you're trying to overcome. Okay, so if we're running a heat pump and it's really cold outside, we have to use more energy to boost that energy to the temperature that would be comfortable. Okay, so we might have a coefficient of 2 rather than 3 that we would get when it's warmer. So how can we arrange it so that we take heat from a warmer source? We can't really change the weather. One option I'll talk about in a minute is what's called a ground-coupled heat pump. We use the ground as the heat source, and the ground's kind of steady temperature all year round. It doesn't get down to freezing. And so that will give us a smaller band of temperature boost so that we get higher efficiencies. Another way would be if we could lower the air temperature that we're trying to warm the house to. And there's a couple ways to actually do that, at least by a few degrees. As we improve the building shell, in particular the windows, as we make that R1 window an R2 or maybe an R4 or R6, that surface is now warmer and we exchange less radiant heat between ourselves and the room surface that makes us feel colder. And so we feel comfortable at a lower temperature with a couple degrees cooler air in the room because we're not losing all that heat to that cold surface. Similarly, we can apply our heating delivery. Instead of heating the air, we can heat a surface like the floor. It's called radiant heating. And that creates a similar effect. It makes you feel a little bit warmer than the air temperature. And again, if you can thereby lower the temperature at which you're delivering heat to the space, you can improve the efficiency, the COP, of the heat pump that's delivering that heat. So there's a few little strategies that we can use taking advantage of the laws of thermodynamics. So one of the things that you might be thinking is, well, okay, if you have one of those gas furnaces with all the ductwork to deliver heat, you could stick a heat pump in there instead. And indeed, that's one way to electrify and decarbonize home heating. But what if you have those crummy little resistance heaters, the baseboards? Well, there's another approach, which is kind of like having a room air conditioner. It's not really a room heat pump, but it's a ductless heat pump where the compressor unit is on the outside of the building, and you just run little half-inch refrigerant lines into the heat delivery units, and they can heat and cool. It's a heat pump. It's reversible. And you can install those in a lot of retrofit situations in place of baseboard heating or in place of whatever's there. And so the ductless heat pump has become really kind of a breakthrough that's enabled the use of heat pump technologies to either replace resistance heat and do electric heating much more efficiently, going from bad electric heat to good electric heat, or to electrify a formerly gas-heated building. Now, if you're thinking, well, I mean, there's other things that we use heat for. We do space heating, but we also heat domestic hot water. And yeah, there's heat pump water heaters. And in fact, you can get a coefficient of performance of 2, 2.5, or 3 with a heat pump water heater. Looks kind of like that unit on the right. They're getting a little better integrated these days. That's kind of an older model. And then what else? Oh yeah, we dry clothes with heat from gas or electricity. And yep, there's heat pump dryers just coming on the market, a fairly new device, but again, a multiple of the efficiency that we used to have with conventional appliances. So there's a whole kind of portfolio of energy savings and efficiency improvements available there. I mentioned the ground source heat pump. Sometimes these are referred to incorrectly as geothermal heat pumps because they're in the ground, but they don't actually extract heat from the ground. They just exchange it back and forth. And so it's taking advantage of the fact that the ground, isn't freezing cold when it's a cold winter day. It's still sitting there at, maybe 50 F, 10 C or something all year round. And so you take advantage of that property of the heat pump, and you get more efficient heating in the winter and cooling in the summer. So the ground source heat pump is a much more efficient, albeit more expensive, way to apply heat pump technology. So those are some of the things that we consider energy efficiency measures. And again, that's only a subset. In order to think of all of the possibilities, you have to really be a geek and go through all of those different end uses of energy and think about the technologies that are available or that might be developed in order to improve their efficiency. And so one of the things that we think about is, as we identify individual measures, we tend to think, well, how much does it cost? What's the levelized cost of saving energy? And we think of like a supply curve or a marginal cost curve where you rank the cheapest to the more expensive. And of course, logic says, well, you should do the cheapest ones. But what we find is that's a little bit selling the idea short, because once you improve the envelope of the building and the efficiency with which you're delivering heat, then it starts to require less equipment to deliver the heat. Maybe you eliminate it entirely. And all of a sudden, not only are you saving energy costs, you're saving on the upfront cost too. And so we start to observe what Amory calls tunneling through the cost barrier. The idea there is if you really get the downstream part of the system super efficient, the upstream part becomes smaller or even disappears, and therefore a whole lot cheaper. And your economics go from kind of diminishing marginal returns to, whoa, this is a good deal to really max out efficiency in this building or this industrial process. And in order to get that kind of improvement, you can't quite look at the energy efficiency measures individually, as I was implying there. You can't kind of go widget by widget. You really have to look at the entire design of the building: shell, equipment, interior, exterior, heating, cooling, lighting, and everything together. We call that type of design approach integrative design. And that's actually the methodology that we teach in the course that we run in the winter and the spring. And this slide is just an enumeration of what we call the pillars of integrative design, some of the ideas that we find useful to realize this approach. And probably the one that makes the most impact in efficiency is number 4, saving downstream. So you go to the very end use. What is it that it's that service that I'm trying to deliver, the cold beer and the warm showers? And how do I change the system so that I need ever less of that? And then those savings multiply upstream. You need less and less, and that's where you get the tunneling idea. But anyway, all of these pillars come into play and can be very useful. One of the things that's sort of obvious is if all this efficiency potential is out there, it means we haven't already done all these things yet. And why is that if they're so attractive from a technological or even a economic standpoint? And so there's a whole literature on this idea, and it's really known as the barriers to energy efficiency. It's all of the things that need to change so that we can actually realize the potential that one can identify as you go through energy uses and identify technical improvements. And I guess the thing that drives all of it is the simple fact that with energy efficiency measures, you generally have to pay up front. You have to buy the more efficient equipment, or you have to spend money to retrofit the window, and your benefit, your savings are accrued over time, maybe for a very, very long time, but you don't get all of that right away. So you have an upfront cost versus a future um, benefit, and therefore you get into the question of, well, how much do you discount the benefit? How does the customer treat that? What's the payback? Or you can define the economic calculus however you choose. But the bottom line is we observe that people don't tend to spend as much money up front for more efficient energy using equipment as would seem to be justified by economics. And there's a whole range of different reasons for that, and many of them we can overcome. One of the most notorious is the split incentives problem. So, for example, if you're renting an apartment, or if you're a business renting commercial space, which is of course very common, you don't really have much incentive to spend money to upgrade the landlord's building, right? No matter how cost effective. And that landlord, well, they don't really have much incentive to lower your bill, right? So nothing happens. And we can talk about 1 year payback. We can talk about whatever cost-effective measure. There's no reason for anybody to do it. So that's a barrier. Okay, that's kind of a simple example. But even in the design process of new buildings, the owner, the architect, the engineer, the builder, and then the eventual occupant, or maybe someone who rents from them, all have their own economic priorities, and none of them are really sending a signal that, yeah, I'll pay for a more efficient building and I'll recoup that in my future lower energy bills. And so there's generally a disconnect even in the design process, not just in the operation of buildings. And then when you observe how people, even homeowners or building owners, choose to make these sorts of investments, they behave as though they demand a very, very high return on investment, which in the financial world indicates that they see these investments, these measures, as being very risky. High risk, high return. Okay, that makes sense, except they're not. Putting insulation in your wall, it's gonna save heat. And so it really has more to do with something like, oh, well, yeah, but I might move in a year or two. So, how am I going to get the savings then? And so there's yet another layer of split incentives and disincentive that results in this observed risk premium for something that's really not all that risky to begin with. And even the information, if I'm going to buy a more efficient heat pump water heater, for example, is it worth what I'm paying? Typically, the customer doesn't have very good information, maybe doesn't even have awareness that the alternatives exist. And in the literature, they talk about search costs. And so this is an example, back when LEDs were a little more expensive than they are now, of, is the homeowner going to go to Home Depot and comparison shop and find the LED that is going to save them, many dollars every year for as long as LED lamps last? I don't know. I've never had one burn out, so I don't even know what that number is. Well, maybe they will, but maybe Home Depot's not carrying the model they have, or maybe they think, oh, $5 for a light bulb, how can that ever pay off? Well, it can, but it's a barrier. And so the bottom line is, as I say, I don't have time to review this whole literature, but it's the flip side of why this potential exists. The potential wouldn't be there if we had already captured it. And so we need to go out and sharpen our pencils and be geeks and find all the energy uses, look for the efficiency opportunities, and then figure out ways to capture them via implementation. So let's talk about that a little bit, because it moves us from kind of the quantitative and policy environment, quantitative and technical environment, into the policy environment. Before we really got into this question of energy efficiency and energy services, the idea of energy policy was typically limited to Well, let's do research and development. Let's invent fracking and let's make solar cheap and let's go find new sources of geothermal. And yeah, we could spend some money on it on the demand side too and energy efficiency. Um, and let's provide information to customers. Let's make sure that they know that there are more efficient light bulbs out there or what have you. And that doesn't get you much actual progress. Um, you might supplement that. I mean, from a standpoint of economic models, a lot of this idea of efficiency doesn't actually exist. But you say, oh, well, if we increase the price of energy, maybe an emissions tax, maybe a carbon tax, that would shift the equation in favor of using energy more efficiently, and it would at the margin, but you'd still be subject to all those barriers that we were just talking about. And so you don't actually get much effect, much impact, much investment in efficiency from higher energy prices. The economic lingo to describe that is that the price elasticity of demand is a very small number, like minus 0.1. And so, yeah, we gotta push a little harder. So there's a range of different policy approaches that have been used successfully to advance energy efficiency. I'll talk about a couple in detail. One is simply minimum energy efficiency standards for equipment, buildings, vehicles, to say you can't sell widget A unless it has at least energy performance above some level. If it's less efficient than that, it's not allowed. And that has the effect of getting rid of at least the lowest efficiency models on the market. Another approach that's been tried in some jurisdictions, including California, is encouraging our energy utilities to not just build power plants and transmission lines, but also to help their customers invest in energy efficiency on behalf of those customers to save energy, reduce bills, and make the overall energy system cheaper and cleaner. So I'll talk a little bit more about that. There's other approaches. For example, in Europe, they use a lot of public procurement to try to jumpstart markets for efficient devices. And there's a whole menu. But I'm just going to look at these two very briefly, just to give you the flavor for how we try to nudge markets and investment in energy efficiency. So standards are pretty simple. It really just does say you can't sell a widget that's less efficient than X. Now, yeah, it starts to get complicated. For example, you could just prescribe the efficiency of every surface and every type of equipment in a building. But that gets a little tedious, and compliance is kind of a pain in the backside. And you don't have that flexibility for tunneling through the cost barrier, right? So some standards, for example, the energy efficiency standards for buildings in California, use a performance approach as well, where it's like, okay, here's the menu of the efficient devices and components for the building. You can just follow that and you'll get a certain level of performance. Or you can do whatever you want and get the same level of performance or better, and you have to do some modeling to show that you've done that. So you have compliance pathways that are simple but tedious and that are more flexible, but that demand compliance. And the things that standards do is it overcomes that information, that search cost, and also on the side of the producer of equipment, the appliance maker, for example, it reduces the risk of saying, well, if you spend a little more money to introduce a higher performance product, will anybody buy it? And so it's like, yeah, they're going to buy it because they can't buy the old stuff, okay? And so it produces a little bit of signal on the supply side as well. And really, it doesn't take much to implement effective standards. The thing is, though, from a political and a consumer preference standpoint, you got to be pretty careful to make sure that whatever you require is going to save the customer money. You can't push the market so hard that some people are not going to be better off. So you have to be pretty conservative, and to figure out what that level is, you have to do a fair bit of analytics. And so in order to promulgate energy efficiency standards, we need an energy commission staff that can analyze the technology, run the numbers on the economics, and figure out what level to set the standards, and then over time update them, generally making them more stringent as technology evolves and improves, so that you're always saving the next year's customer money at the point of purchase. So just one little history snapshot here. This is for refrigerator freezers in the US, going back again to the bad old days. 1974, the Warren-Alquist Act in California was the first state-level energy policy that included energy efficiency and instituted the first appliance efficiency standards. And around that time, a refrigerator was using about 2,000 kilowatt hours a year. And over time, the standards have gone from California to nationwide, and they've been gradually tightened. They took a little pause in the 1990s because that's when we were replacing the refrigerants to get rid of the ozone depleting compounds and using alternative refrigerants. And the industry said, hey, time out, we can't do too many things at once. Give us a break on efficiency and we'll replace the refrigerants. Okay, guys. And then they resumed. But over that time, the average size of refrigerators, the blue line, has increased somewhat. The average cost has actually declined, so we haven't been taking money out of the customer's pocket. The green line is average cost. And the energy performance has improved by a factor of more than 4. So we've gone from 2,000 kilowatt hours a year to less than 500, and we're a little bit lower now. And so that's okay, 1,500, 1,600 kilowatt hours in a fridge, big deal, right? Okay, multiply that by what, 100 million refrigerators out there over time, and you get to something like 40 large, full-size coal-fired power plants that you don't build, you don't fuel, you don't finance, you don't pay the bills, you don't incur the emissions, you don't have the global warming impact. So that's megawatts in a big way, just from the simple refrigerator driven by standards. Nobody knows that they exist. Nobody knows that their fridge used to use 2,000 kilowatt hours. Nobody knows they now use 500 and they're saving, $150 a year because of that. Well, sorry, $500 in California. So it's a pretty unqualified success. And there's other cases. These are voluntary standards for TV monitors that have also signaled significant reductions in energy use and performance, and it can be applied to lots of different types of individual energy-using appliances and devices. Lighting is one, as I say, lighting's gotten a lot easier recently because of the LED technology, but for a long time, California's building energy performance standards, so-called Title 24 standards, have had lighting efficiency standards, and this is a place where you can't really prescribe the technology too precisely. Rather, it's a performance standard where they say, okay, for a given area of whatever type of space, is it a hospital, office, retail, whatever, you can't install more than X watts of lighting power, so you better figure out how to make each watt do more by improving its efficiency, whether it's in the hardware that controls the space itself, daylighting, what have you. But different types of buildings have different needs, and so the standards are actually tailored to each of the different columns there with different values depending on what they're trying to achieve. And then over time, they were gradually tightened, made more stringent. Again, as technology evolves and design improves, the numbers get a little bit lower. And one of the nice things about that is when you have efficiency standards on this kind of a basis, it gives you a baseline. If you're going to do any further efficiency improvements, and I'll talk about that in a minute, you know what you're measuring your improvement from. You have a baseline against which to compare. So Bottom line is standards are a great way to get rid of the least efficient products and systems on the market. But that's only part of the market. If you think about some arbitrary technology and a range of adoption of more efficient technology over its lifetime, it has the typical early adopters in the chasm, and then the mass market, and then the late majority and the laggards. And the codes and standards are really meant to, move the laggards. Like, no more lagging. Let's get rid of the least efficient equipment and make sure that everybody's at least within a reasonable span of the market. Meanwhile, at the other end, we're using our R&D programs. We're implementing emerging technology programs to try to commercialize new ideas that are just reaching the market. And then in the middle, there's a whole area where, okay, they're mature technologies available in the market, but they're not such a no-brainer that we can just mandate their use against other less efficient ones by standards. We can't be sufficiently confident that everyone will win. And so again, standards have to be a little bit conservative. And so in between, there's a whole lot of room to try to nudge customers into greater efficiency that will mostly be expected to be cost effective. And that's where we've seen the use of energy efficiency programs by energy utilities to try to help their customers reduce their bills by reducing consumption and improving efficiency. And so there's a whole range of approaches. And again, the kind of traditional approach, utility sort of customer service, if that's even a thing, is providing information, maybe providing referrals to contractors, maybe even a free energy audit. We'll come to your house and we'll look around, we'll find the places that aren't insulated, or the leaky windows, or the busted appliances, or the out-of-date lamps, and suggest measures that you might do to improve them. Turns out that's, again, necessary, but not really sufficient to get much done in terms of efficiency improvement. If we really want it to happen with the customers, you kind of have to bribe them. You have to provide financial incentives. And the simplest and to date most effective one has just been simple rebates, just buying down the first cost of more efficient equipment. That's driven a lot of energy savings in the states where utilities have been encouraged and incentivized to do that, both in the residential and commercial sectors. Mostly in the more affluent part of the residential sector, I would say, where people have the cash to make that expenditure and then collect the rebate. It's not as straightforward at the low income part of the market, and so we're still learning how to do a better job there. One recent development in terms of efficiency incentives has been to move from working with a customer to go upstream and work with vendors or even manufacturers, providing them incentives to stock the market with more efficient widgets, and you get a lot more leverage on your incentive that way. Another approach would be, well, what if we offer financing, low interest loans to customers to install efficiency measures? That doesn't work. Basically, it's been a complete flop in just about any place it's been tried, because people don't want debt on their balance sheet or their credit report just to save some money on their energy bill. It just doesn't happen. However, more recently, a little variation on that theme has been much more successful, where we use more of a leasing program. Some places it's called pay as you save or inclusive utility finance, on-bill financing. And the idea is you're not making a lease or loan to the customer, but to the premises. So it sticks with the meter, not with the person. So it's not on the credit report, and it's not on their balance sheet as a business. And that makes it much more attractive. And also, if they move, they don't have to worry about it. And interestingly, and kind of surprisingly, these programs have gotten a lot of traction recently with not usual suspects, with like rural cooperative utilities in the Midwest that are not known for their progressive green credentials, but actually kind of like the idea of saving their customers money, if they can do it in a way that you have positive cash flow from day one, because you're repaying that debt via the lease on your utility bill, but the payment is less than the energy savings that you're achieving. And so you have positive cash flow from day one. You have no debt on your balance sheet or income statement, and the obligation stays with the house. It doesn't move with you. And so all of a sudden, we finally found a way to do efficiency financing that is getting traction with low-income customers, as well as creating a new option for other residential and commercial customers. Kind of an interesting breakthrough, really. So again, a lot of this work is actually kind of nerdy geek work of finding the energy uses, finding the technical opportunities, and then analyzing to say, what's the potential? And the way that we typically categorize the efficiency potential, the resource that we're trying to capture, is first we just say, well, how much can the technology save? And we call that the technical potential. And you can imagine that's a lot. You can go out and find technologies that will drive your energy use to pretty close to zero just about anywhere. But at what cost? Well, then we sharpen the pencil and say, okay, how much of that potential is cost effective? How much of it has a levelized cost that's comparable to or less than what you'd buy the energy, for example? And we call that the economic potential. All the measures that are cheaper than the chosen measure of avoided cost or break-even cost. That's the economic potential. It's the subset of technical potential. Well, now you can't get all of that through these programs. You're not going to get every single customer and every single widget. And you certainly can't get all of it now, this year. And if you're talking about efficiency as a resource, you're a supply utility, and you're going to say, well, we'll do enough efficiency, we don't need that extra thermal plant in year X. Well, you better be pretty confident that you're actually going to achieve these savings by year X, maybe a little more to be conservative. And so what's the achievable potential? What's the subset of the economic potential that you can achieve through real programs that you have experience with, and you're providing incentives and marketing and all the things you need by a given year? And once you have a handle on that, you have the achievable potential. Now you have an efficiency resource that you can use your negawatts of efficiency to replace the megawatts of supply. And probably the most successful and certainly the best documented practitioner of this is in the Northwest. The Northwest Power and Conservation Council, ever since about 1980, has been producing every 6 years or so a resource plan to say, how do we keep the lights on and the economy running here in the Northwest in the electricity sector with a combination of our old hydro dams that we built back in the New Deal and other supply side, maybe increasing renewables, and explicitly the demand side energy efficiency resource. And consistently since the 80s, including a much more recent plan, they've found that over 50%, and in the recent plan, more like 80% of the new energy resources that they expect to call on in their least cost plan are not megawatts, they're negawatts. There's efficiency resources to be captured. And remember, this is after they've been doing this stuff pretty aggressively, going on 40 years. So we haven't diminished or exhausted the resource. Rather, it's renewing because of technology, because of design, because of new business models. And so the Northwest is finding that the negawatt resource has been and continues to be a really important contributor to keeping energy costs down and minimizing emissions in the energy system. A number of states have standards. You're probably familiar with renewable portfolio standards, like you got to have 30% wind and solar in your mix. Well, most states tell the utilities they got to have a certain amount of efficiency savings year by year in order to satisfy their regulatory mandate as well. So we have energy efficiency resource standards analogous to renewable portfolio standards. And so as a utility, what that enables you to do, if you take it seriously, is to create a portfolio of approaches to tap resources on the demand side of the meter, not just power plants and power lines, but influencing demand by reducing it through energy efficiency, by shifting it in time through what we call demand response or peak load management programs and technologies, and increasingly energy storage, where you put energy into batteries when it's cheap or surplus, and then use it when you need it. And today we're adding another element. Remember the good heat pumps that we can replace gas heating with, and also EVs. We're adding electrification, shifting fossil fuel energy uses into electricity supply. And so there's a whole portfolio of efficiency, demand response, storage, electrification, all those things together we refer to in a very ugly acronym, demand side management, DSM. But it's the part of the portfolio of utility resources, if you consider a comprehensive portfolio, that is not just the supply side. And as an example, if you're putting in heat pumps, good electric heat, every time you replace that gas furnace with a heat pump, you're going to drive up your electricity demand. Even if it's efficient, you're going to have more electricity because you didn't have any before. It was gas. Well, you had the fan. That was it. So, okay, well, we need more supply. Well, wait a minute. We got more heat pumps. Let's put some in the bad electric heating, resistance heated buildings. And now you're using electricity, but you're using less than you were before. So you're decreasing the call on the demand. And so you can have a whole lot of efficiency and a whole lot of decarbonization and electrification and not necessarily influence or increase, at least, the overall electric demand. And it works in a number of different end-use sectors as well. Okay, so what's the point? What does this have to do with the overall decarbonization? Well, that's an example. If you can do both less electricity and switching to gas to efficient electricity with heat pumps, that's a pretty good gain in terms of decarbonization. The bottom line is decarbonization is calling on us to decarbonize our power supply, and we're making good progress there. And once that happens, it becomes attractive in terms of decarbonization to electrify fossil fuel uses like cars and trucks, like heating with gas to good electric heat in heat pumps. But to make the overall enterprise work and move fast enough and be affordable, capturing the energy efficiency resource in each category and sector of energy use is also essential. Think about an individual building. This is the Bullitt Center in sunny Seattle that was, at the time, and maybe still, the largest net zero energy commercial building in the country in sunny Seattle. So like, what's up, California? Anyway, as you can see, they had to exaggerate the area of the roof to get enough solar to work in Seattle. But the bottom line with an energy, a net zero energy building is the simple equation that says to get to net zero, you got to produce more than you use, okay? So how much can you produce? Well, what'll the roof give you? Even if you cheat a little bit, like in this building in Seattle. In order to achieve net zero, you have to manage the load, the demand, the energy use through an efficient shell, through efficient equipment, through efficient controls and operation. And so the key to getting the balance in an energy net zero building is efficiency on the demand side. And so that really applies to the whole economy as well. If you think about, okay, well, we're going to install a lot of solar power, wind, geothermal, biofuels, what have you, like, can you get that fast enough? Well, if your demand is growing exponentially at the same rate you're installing your renewables, you're not making in much headway on replacing fossil and CO2 emissions. And so the efficiency resource is complementary to the other two pillars of decarbonization in terms of decarbonizing power and electrifying. And it enables you to get there faster in terms of backing out the fossil and CO2 emitting supply sources. It also gives you a cost-effective alternative to getting way up on the supply curve of your supply sources, or needing carbon capture or other exotic ways to reduce emissions that are bound to be expensive and have negative co-benefits. And so overall, the efficiency resource is the balancing act that you need to enable speed and affordability and manage the environmental impact of all those renewables and the materials that go into them, which are a whole lot less than the fossil fuel supply chain, but still not zero. And so the leverage that you get from successful energy efficiency improvement is really an essential pillar of that decarbonization strategy, right alongside clean power and right alongside electrification. And up until very recently, most of the decarbonization that we've achieved has actually been through the demand side improvements in efficiency. And it's been fairly recent that we've actually started to make some headway on the supply side. Thank you, wind and solar. And our friends at the American Council for Energy Efficient Economy, which is, as you could guess, a think tank that focuses on energy efficiency, they were looking at some of the studies of deep decarbonization. How do we go far and fast in replacing fossil fuels? And what they found is there's a real range in how they treat efficiency. They generally assume some continued improvement kind of at historical rates or maybe a little bit more, but they don't really treat it as an option to say, well, what if we put the pedal to the metal on this stuff and try to capture all the cost-effective resources? And so the ACEEE started to look at that, and they found, you could get about halfway to total decarbonization just with demand-side efficiency. You still need renewables, you still need electrification, but it gives you a much more robust portfolio. And the pie chart shows their analytics of kind of the different approaches that you could use to capture the efficiency resource. And as you can see, they found the silver bullet was, there's no silver bullet. They found that you really need a whole range of different approaches and technologies in the different sectors, in different policy approaches. You really need, again, to go back and sharpen your pencil and be a geek with the rest of us, figure out where those end uses are, what the technical improvements could be, how much they cost, and then how to capture them and nudge customers to install them. And so bottom line, the efficiency resource is essential and it's big, but it's spread all around the economy and we got to go find it. So I guess the flip side of all that is what happens if you don't do this? Well, you get Texas. So you probably remember, 3 winters ago, there was a real debacle in terms of unprecedented winter storm that hit Texas and knocked out the power system in most places. And as you'd expect, there was a lot of finger pointing. The governor blamed the wind farms, which had a very short-lived shortfall in supply. They probably did the best of any of the resources. There was some 18 plus gigawatts, you guys know what a gigawatt is, of gas-fired generation plants that called in sick. Some for technical reasons, but a lot of them, it was just that they were selling so-called firm power, that is guaranteed supply, but they were buying their fuel, the gas, non-firm, that is, they're flying standby as available. Guess what? It wasn't available when every house that used gas needed to be heated to the max. They lost a couple gigawatts of nuclear plants that were unavailable, and then once they tripped, took more than a week to get them back online. But what no one talked about was the demand side and the inefficiency of buildings, especially in Texas, that increased demand over 30 gigawatts, and it would have been more, but then the power went out because they have really poorly insulated, inefficient buildings heated with bad electric resistance heat, very few heat pumps. And that cold snap triggered a huge spike in demand that it didn't matter who was calling in sick on the supply side. They weren't going to meet that. And if they had California's energy efficiency standards, they'd actually save more energy because of the more extreme climate. And they wouldn't have had this brittleness of their system due to such an extreme spike in demand caused by a week of bad weather. So just to say the efficiency resource isn't just about the environment. It's definitely about saving money. It's also, though, about resilience and robustness and security of the energy system. And so that's kind of the sermon. We see efficiency as the cheapest, cleanest, most secure energy resource, a key pillar alongside clean power and electrification for decarbonizing the energy system. I talked briefly about and would be happy to spend a quarter rearranging your mental furniture around integrative design, which we see as the ideal way to find energy efficiency improvements. That said, there's many cost-effective measures available now, everything from LED lighting on. We have to overcome the market barriers to adoption through policies and programs. There's some examples that I pointed to of codes and standards and utility programs. There's lots of other ways, and hopefully we'll come up with some new ones to capture that resource going forward. So that's the party line on energy efficiency. Thanks for your attention.